back to population growth and the logistic curve. In our previous module, we defined e to the x, and we defined it like this. In this module, we're going to justify why we write e to the x just like it's a 2 to the x or a 3 to the x. The reason we do this is because both of these things obey the index laws. They both obey these properties down here that if I take, say, 2 to the power m and 2 to the power n, then that's equal to 2 to the power m plus n. I just have to add these exponents. And e to the x behaves the same way. We'll see that later on in this module. Let's explore these powers of 2. And I've got in this table some exponents, n, and some powers 2 to the n. Hundreds of years ago, well, back in the 16th century, Napier originally came up with huge tables of things like this. And he'd populate all the numbers between, well, all the numbers in between. So he'd have 0, a half, he'd have a quarter, a third, a sixth, a hundredth. He'd produce these huge tables of powers of 2. Why would he do this? Well, it's because back in those times, and in fact all the way up to the 20th century, this is how people would multiply numbers. If you wanted to multiply this number here, so 1.414 times by this one over here, 2.828, you would take your book, which contained tables and tables of numbers and their corresponding powers. And here we have the New South Wales Department of Education mathematics tables from 1975. And we could look up that 1.414 is approximately equal to 2 to the power 1/2. And the second number, 2.828, is approximately equal to 2 to the power 3/2. And then we use our use our index laws to say that this here is just equal to 2 to the half plus 3/2, which is 2 to the 2. And then I now put this back into my lookup table and discover that 2 to the power 2, well, that's just 4. So these lookup tables are extraordinarily powerful things which became redundant as soon as we had pocket calculators, but they were very useful for hundreds of years. And this calculation demonstrates the use of these index laws for 2. But it's not yet clear that we can apply the same laws to something like this, where e is defined as this limit. Our objective in this module is to prove the index laws for e to the x, but in order to wield our definition of e to the x, we need some properties of limits, and I will remind you of these properties here. Recall that the limit as n goes to infinity of f of n is the same as the limit as n goes to infinity of f of n plus k for some constant k. And that's the same as if I was to multiply this n by k as well. And I won't prove this for you, but I'll demonstrate it with an example. Suppose we have the function 1 on n, and we choose our fixed constant k as 2. Well, the sequence f of n as n goes from 1 to infinity is this sequence here. And as we can see, these terms are approaching 0, so this limit is equal to 0. What happens with f of n plus k? Well, f of n plus k is this sequence, or f of n plus 2 from n equals 1 to infinity is just the sequence, well, like if k is 2, then when I start with n equals 1, this is f of 3. So the first term is 1/3, and then when n is 2, then I get 2 plus 2, which is 4, so that's 1 on 4. And so on. And this sequence also approaches 0. So adding a fixed constant k to this just shifted our sequence along. It did not change what its eventual limit was. So we can also say that this limit is 0. And what happens now if I multiply n by 2? So f of k times n equals 1 to infinity. Well, that's just equal to, when n equals 1, this is f of 2, so the first sequence here is just, or the first element of this sequence is a half. When n is equal to 2, this is 4, so I get 1/4. When n equals 3, I get 6, and so on. So really, I'm just picking out every second term of this sequence. And because each term of those in this sequence goes to 0, so does every second term of that sequence also go to 0. So the limit is again unchanged. So these are some simple things you can do with limits that do not change the value of the limit. You can add a fixed constant in there, and you can multiply the n's by a fixed constant as well. And this will not change the value of the limit. And this is what we need in order to manipulate our definition of e to the x. With our properties of limits in hand, we are in a position to prove the index laws for e to the x. I've listed out the things we're obliged to prove here. We are obliged to prove that e to the m times e to the k is equal to e to the m plus k. We are also obliged to prove e to the m to the power k is e to the mk, and that e to the negative 1 is 1 on e. And I've listed this out in the order of difficulty. This one is somewhat tricky to prove. This one here is a little bit tricky to prove. And this one here is the least tricky to prove. So I will do the one of medium difficulty, and I'll leave the others for you in the activities. All of them come down to using the properties of limits from the previous slide. So if you have those in hand, then you have all the tools necessary to prove these identities. Great. Let's get cracking with this one. E to the m to the k. Well, I'll break out the definition of e to the m first of all. This is the limit as n goes to infinity of 1 plus m on n to the power k. And I'll bring the k inside. So this is the limit as n goes to infinity of 1 plus m on n. Oh, there's an n there. To the power nk. Excellent. And now I'll multiply the top and bottom here by k. So that's the limit as n approaches infinity of 1 plus km on kn to the power nk. Which I claim is the same as the limit as n approaches infinity of 1 plus km on n to the power n. And I claim this by virtue of the limit laws that we had on the previous slide. And happily, this here is just e to the km by definition. Behold, one of the 3 index laws for e to the x. I'll leave it to you to prove the other 2. But they follow mostly the same pattern where you have to manipulate this limit somehow and then use one of these properties of limits. So far we've taken an historical approach to the number e. We've defined it as a limit, and we've shown that it has certain nice differential properties. For example, it is its own derivative. And then in this module we showed that it behaves according to the index laws. Excellent. Let's now contrast this with another method of introducing the number e as the solution to a differential equation. Here is the function f of x equal 2 to the x. Let's talk about its derivative. The derivative is given by first principles as the limit as h approaches 0 of f of x plus h minus f of x divided by h, which is the limit as h approaches 0 of 2 to the x plus h minus 2 to the x divided by h, which is the limit. Well, I can actually split this up. I can take out a common factor of 2 to the x, So that's 2 to the x times by whatever's left over, the limit as h approaches 0 of 2 to the h minus 1 over h, which is quite an interesting way of splitting this function up, because I have here the function itself, and over here I have some constant. This number here, whatever it is, doesn't depend on x. It does depend on 2, but it doesn't depend on x. So I'll write this out as d dx f of x is equal to f of x times by some constant k. And we'll put a big box around that, because that's such a lovely differential equation. The derivative of a function is a constant times itself. And one way of introducing the number e is to say that the number e is the base whereby this constant is equal to 1, which I find inferior to the historical way of introducing to the number e, because with the historical way we actually have an explicit definition of what e is, rather than a supposed solution to a differential equation. So I much prefer the historical approach to the number e than this style of approach. Let's do one more thing. Let's find out what k is. I can see from my function e to the x over here, at some point it will pass through the number 2. Let's call that point c. So since 2 is equal to e to the c, and I could find c by looking up my New South Wales Department of Education table of math. Since e is equal to 2 is equal to e to the c, then I could say that d dx of 2 to the x is equal to d dx of e to the c to the power x. Aha! And we know that e to the c to the power x is d dx of e to the cx. And I know how to take the derivative of e to the power x, or something of this form. That's just c e to the cx, which now is just c times e to the c to the x, which is c times 2 to the x. Behold, the derivative of 2 to the x is just c times 2 to the x, where c was the solution to this identity here. Hence we say that c is equal to this constant here is called the natural log of 2. That concludes module 2. In the third module, we're going to be using our function e to the x to do something quite wonderful, which is population modeling. So it's not too much of a stretch to go from something like e to the x to the logistic curve, which is really just the reciprocal of e to the x plus a constant. But the logistic function also has lovely differential properties, similar to that of the exponential function, which we will see in module 3.